Hey guys, tonight we're heading somewhere wonderfully far away, about 2.7 billion miles out, give or take, where the winds howl louder than a stadium full of leaf blowers and the clouds drift by like ice sculptures on a lazy river. We're talking about Neptune, a lonely deep blue gas giant so far out it barely even sees the sun. And frankly, it doesn't seem to care. You probably won't believe this, but for all its chaotic energy, Neptune might just be the most chill planet in the solar system. It's the kind of place where storms the size of Earth quietly appear, wander around, then vanish without explanation, like shy cosmic tourists who decided not to leave a review. So before you get comfortable, take a moment to like the video and subscribe, but only if you genuinely enjoy what I do here. And if you're in the mood, drop a comment with your location and local time. I love seeing where and when you're all tuning in from. Now dim the lights, maybe turn on a fan for that soft background hum, and let's ease into tonight's journey together. You drift through the solar system like a passenger in a silent subway car that only moves forward farther and farther from the warmth of the sun. Mars glows rusty and impatient. Jupiter flexes with thunder. Saturn poses dramatically with its rings. And then out near the edge, Neptune waits. Neptune isn't flashy. It doesn't have the close-up glamour shots like Mars, or the violent daily updates like the sun. No, Neptune is more elusive. It keeps its secrets folded neatly beneath layers of blue. Its storms don't shout. They glide in and out of existence like they've got somewhere more important to be. And here's the first odd thing. Neptune's a windy beast. The fastest winds in the solar system whirl through its upper atmosphere, 200 miles per hour. That's faster than a commercial jet, faster than any hurricane Earth has seen, faster than your cousin Tim's excuses for not showing up on time. Yet somehow, Neptune manages to give off an air of serenity. The clouds swirl, yes, but from a distance, the planet looks like a calm blue marble, floating in the dark. It's like watching a ballet from 10 miles away and being told it's actually a riot. You stare at its soft, deep blue surface, if you can call it that. There's no ground to land on. Neptune is made almost entirely of gas and icy materials, hydrogen, helium, a dash of methane for color, and some sciencey mystery ingredients the periodic table doesn't care to label clearly. You wouldn't want to stand on Neptune. Not because it's hostile, though yes it is, but because there's nothing solid to stand on. You just keep sinking, probably forever. The light here is dim. The sun is a pinprick in the sky, still bright but distant. The shadows are long but oddly soft. Imagine a twilight that never ends, a moody dusk, stretched across an entire planet. You might start whispering, just because it feels like the kind of place that deserves it. But despite its ghostly quiet, Neptune is busy inside. It radiates more heat than it receives, twice as much in fact, and no one really knows why. It's like that one coworker who shows up early, stays late, and still never explains what they're working on. Scientists still argue whether this extra heat comes from leftover energy during formation or from some sneaky internal process we haven't identified yet. Either way, Neptune's got a heater running under all that blue. And then there are the storms. They're the real divas of this planet. The most famous, the Great Dark Spot, an Earth-sized storm spotted in 1989 by Voyager 2. And then, not spotted ever again. It was there then, it wasn't. Poof. No public statement, no farewell tour. Just gone. And this isn't a one-time thing. Neptune storms tend to appear and vanish with very little explanation. like intergalactic soap bubbles that don't respect the weather forecast. There's a reason Neptune is the poster child for atmospheric weirdness. Unlike Jupiter, whose great red spot has been throwing a tantrum for at least 350 years, Neptune's storms are more like introverts. At a party, they show up, maybe make a loop around the room, then quietly leave before things get too loud. You can almost imagine the other gas giants shaking their heads, wondering where Neptune's sense of drama went. One of the reasons these storms are hard to track is that Neptune rotates quickly once every 16 hours. That's faster than Earth, despite being nearly 4 times as wide. So clouds and storms whip around the planet, changing shape and position almost constantly. From afar, it looks like someone took a slow-motion video of cotton candy being stirred by invisible fingers. But here's the truly bizarre part. All of this, the winds, the clouds, the vanishing storms, happen under almost no sunlight. Neptune gets only 1/900th height the solar energy Earth receives. It's like trying to power a Ferris wheel with a single tea candle. And yet Neptune keeps spinning, swirling, and causing sleepless nights for planetary scientists everywhere. You drift closer to the planet's upper atmosphere, where the winds are slicing through the methane-rich haze like whispered threats. There's no smell here, no sound, no pressure on your skin, but somehow you know the place is alive with motion. The clouds form bands, sometimes white, sometimes dark, always moving, with a grace that feels out of place in such a violent environment. Some researchers suspect that the methane absorbs red light, letting the blue colors shine through, hence Neptune's rich hue. Others think deeper chemical processes may be involved. Scientists still argue whether Neptune's color comes only from sunlight and methane, or from something exotic brewing beneath the clouds. Either way, the planet has more drip than a watercolor painting left out in the rain. And so, you float, watching, listening even though there's no sound. Neptune doesn't roar. It whispers. It doesn't explain itself. It simply continues. You drift a little closer now into the upper levels of Neptune's atmosphere, where things start to get oddly aggressive. Not that you'd notice at first. Everything still looks soft. Those clouds still float like brushed velvet, and there's no thunder to scare you awake. But beneath that calm exterior, Neptune is quietly throwing a fit that would rip the shingles off your house and send your groceries into orbit. Let's talk wind. Not a breezy Sunday in the park kind of wind. No. Neptune's winds hit 1,200 miles per hour. That's Mach 1.6. It's faster than fighter jets, faster than sound, faster than any hurricane Earth could even imagine. If the atmosphere of Neptune ever auditioned for a role in a Fast and Furious sequel, it would win the part and crash the set on the first take. And what's powering all of this, no one knows for sure. You'd think such brutal winds would need a strong push from the sun. But remember, Neptune gets about the same solar energy as a lava lamp under a dying flashlight. Scientists still argue whether these winds are driven by internal heat rising through Neptune's layers or by the sheer awkwardness of the planet spinning so quickly. Maybe Neptune's just venting some deeply buried emotional turbulence. After all, it was demoted to farthest planet after Pluto showed up with an attitude. What we do know is that these winds create fierce jet streams. Not just one or two polite airflows like on Earth, but multiple stacked like layers in a cosmic croissant. They zip around the planet at different latitudes, often in opposite directions. The result: shear zones, places where the winds collide or slide past each other, like two dancers in a dark room who forgot the choreography. You'd expect chaos, But somehow, it all manages to flow in a kind of hypnotic rhythm. But here's where Neptune really shows off. These winds aren't just horizontal, there's vertical movement too. Heat rises from within the planet. Yes, somehow there's heat down there, and it pushes methane-rich gases upward. These gases cool and condense, forming icy clouds that sparkle faintly in the blue light. You've got updrafts, downdrafts, vortexes spinning sideways, all quietly raging beneath a sky that never fully lights up. And then to top it all off, these layers of gas, hydrogen, helium, methane don't even mix evenly. There are gradients, pockets, and what some scientists call convective cells. That's a fancy way of saying blobs of warm stuff go up, blobs of cool stuff go down, and nobody's really in charge. It's like a lava lamp designed by someone who really needed a nap. Now, if you were floating in Neptune's upper atmosphere, somehow immune to pressure cold and the awkwardness of physics, you'd see something magical. White clouds made of frozen methane crystals skating above deeper bands of blue. Beneath them, darker patches twist and stretch, hinting at more powerful storms brooding far below. And if you looked really closely, you might catch one of those storms, making a break for it, hurling itself across the planet like it's late for a weather conference. One of the weirdest things. These storms are often more stable in the southern hemisphere. Scientists still argue whether that's because of how the jet streams are arranged, or if Neptune's magnetic field somehow favors storm formation down south. That's right. Neptune even has weather preferences. Storms apparently like to travel in style. But even with all this madness, there's a kind of grace to it. The clouds don't rush. They glide. The jet streams aren't jerky. They spiral. It's like Neptune took all the chaos of a planet-wide hurricane and wrapped it in silk. You wouldn't hear a thing. No thunder, no clatter, just silent motion, masked in beauty. One mainstream fact worth remembering: those clouds, they're about 200-degree Urucrus. That's not a typo. That's 70 Kelvin. Your average freezer back home would be laughed off Neptune. And yet somehow, chemical reactions still happen, storms still spin, and winds still howl. The laws of physics don't break on Neptune, but they definitely get bent like a spoon at a magic show. Now, for a quirk. There's a theory, admittedly niche, that the friction from Neptune's supersonic winds might generate static charges in the upper atmosphere. Think lightning, but polite, and probably very confused. It hasn't been confirmed, but researchers with way too much time and not enough telescopes think there could be crackling events that happen up there, tiny bursts of plasma electricity snapping through the clouds like interstellar pop rocks. And here's something even more speculative. Some fringe thinkers wonder if Neptune's chaotic wind patterns might shift in regular cycles, almost like seasons, but glacially slow. Neptune's year is 165 Earth years long, so if it has seasons, they take decades to change. We may have only seen one sliver of its long, lazy weather mood swing. Imagine watching just one frame of a movie and being told to review the plot. That's where planetary scientists are with Neptune right now. Still, there's something comforting about all this. Despite the science, the wind speeds the massive energy. Neptune seems content to keep swirling without any intention of explaining itself. It doesn't roar. It doesn't flash. It just keeps moving. Slowly, smoothly, silently. So you sit back or float back and let the view take over. The planet turns. The clouds stretch. The winds rage quietly below. You can't feel it, can't hear it. But somehow, you know down there, the fastest winds in the solar system are humming a tune no one else has ever heard. You hover just above Neptune's equator, staring down at a memory, a big brooding circle swirling across the gas giant's surface. Or at least you would be staring at it if it hadn't ghosted humanity decades ago. This, dear listener, is where the great dark spot used to live. A storm the size of Earth that just evaporated and left behind only questions. In 1989, Voyager 2 took a lazy flyby past Neptune, our only in-person visit to the planet to date. It wasn't a long encounter, and Voyager didn't exactly linger for tea, but what it captured left scientists scratching their heads. There it was, the great dark spot, a mysterious oval-shaped storm system churning with such power that it should have shaken the whole atmosphere. But instead, it just spun quietly, surrounded by bright white clouds, like a storm wearing a frosted halo. It looked like Jupiter's great red spot's moody cousin. Same shape, similar scale, same swirling vibe, but less theatrical, less red, more mysterious. And Neptune, being Neptune, didn't give much away. The storm didn't come with thunder or drama. It wasn't flinging debris across the atmosphere or tossing lightning bolts like a Greek god. It just spun in near silence. And then just 5 years later, poof, gone. This is where it gets weird. In 1994, when the Hubble Space Telescope turned its lens toward Neptune again, the spot wasn't there anymore. No fanfare. No grand farewell. Scientists still argue whether it dissipated, sank into deeper layers of the atmosphere, or if it just shape-shifted into a new weather system and politely excused itself from our view. It was as if Neptune had performed a celestial vanishing act, and nobody could figure out where the trapdoor went. And it's not the only one. Since then, multiple dark spots have been observed, and each one seems to follow the same pattern: appear, drift westward, maybe wobble a bit, and then fade away without a trace. Some last for years, others for mere months. It's like a rotating cast of atmospheric actors that never stay for the encore. One recent spot in the Northern Hemisphere, spotted by Hubble in 2018, also began to fade. But before it vanished, it did something new. It reversed direction. That's right. It stopped drifting west and started going east. That's not just meteorologically strange. It's the planetary equivalent of getting halfway through a hike, spinning around, and announcing you've decided to walk backward for no reason. You can almost imagine these storms talking to each other. All right, I've been here long enough. Your turn, Steve. We've tried modeling them, of course. Simulations attempt to recreate these storm systems, but Neptune doesn't play nice. The models often fall apart or produce weather patterns that don't match what we see. Scientists still argue whether these dark spots are shallow vortexes that form in the upper atmosphere, or if they're deep, massive structures that extend thousands of kilometers downward. Both options are unsettling. One suggests storms can blink into existence at high altitudes with no warning. The other implies enormous weather systems are brewing deep within Neptune, only occasionally surfacing like a whale exhaling before diving again for a century. Want a quirky tidbit? One dark spot was once observed to have a small, bright companion cloud, what researchers lovingly called a companion cloud. How romantic. This fluff ball of methane ice hovered just ahead of the storm for weeks, like a cloud with commitment issues. Scientists suspect it formed due to upwelling air from the storm, but no one can be sure. The cloud eventually drifted away, either bored or emotionally unavailable. Another peculiar thing: these storms tend to form around 20-30 degrees latitude, both north and south. Why nobody knows. Maybe it's something to do with the balance between Coriolis forces and jet stream positioning. Or maybe Neptune just has favorite spots, like how your cat always chooses that one sunny patch on the carpet. But perhaps the most frustrating part of all this is how little data we actually have. Voyager 2 gave us about 5 days of close-up storm watching. That's it. Everything since then has come from telescopes orbiting Earth, peeking across billions of miles with limited resolution. Imagine trying to study hurricanes on Earth by squinting through a telescope from the moon. That's the level of precision we're dealing with. And yet, despite the fog of uncertainty, one thing's clear. Neptune's dark spots aren't just pretty patterns. They're powerful, complex, and deeply mysterious. They rise, they twist, they vanish. Sometimes they leave no trace. Other times they birth odd clouds that don't follow the rules. Each one is like a haiku, written in methane and velocity, beautiful, fleeting, and deeply difficult to interpret. So you watch the atmosphere roll by beneath you. A pale sun hangs low on the horizon. The clouds continue their silent ballet. And somewhere, below the visible haze, you wonder if another dark spot is forming right now, one we won't see for years, one that might disappear before we even know it existed. The quiet drama continues. Neptune spins its secrets intact. Still floating, you descend a little into Neptune's sky, not too far, just deep enough to feel the layers shift around you. And oh, are there layers? Neptune's atmosphere is like a cosmic parfait. If parfaits could rotate at 1,200 miles per hour and occasionally explode into diamond rain. At first glance, the planet seems blank, just soothing endless gradients of blue. But stare a little longer, and you begin to see the delicate mess of its structure. There are bands, swirls, spots, and cloud decks stacked like lazy pancakes. It's polite chaos. Neptune is a hot mess in a cashmere robe. Up at the top, you've got the stratosphere, a hazy region where sunlight, what little there is, stumbles in and hits molecules of methane. Methane loves to absorb red light, which is why Neptune glows such a rich, deep blue. That color isn't just decoration. It's science, with a stylish flair. But scientists still argue whether the color comes solely from methane, or if there's another unknown chemical pulling a sneaky filter trick on us. Either way, Neptune has nailed its aesthetic. Just below that, a region packed with methane ice crystals forming the planet's high-altitude clouds. They're not just floating aimlessly. They ride the jet stream, stretching and twisting into elegant formations. Sometimes you'll see tiny white streaks flit across the blue background, like exclamation marks in an otherwise sleepy novel. And when sunlight hits those clouds just right on the rare occasion it reaches that far, you might even see a faint glimmer. A twinkle. It's subtle, but it's there, like frost catching moonlight. There's even a speculative theory, not confirmed, but charmingly persistent, that small, reflective crystals, perhaps even diamonds, could be forming deep within Neptune's atmosphere. Yes, actual diamonds. Not enough to start a jewelry business, but enough to make Neptune the sassiest planet at the cosmic gala. Drop a little deeper, and the vibe changes. Pressure increases. The clouds thicken. It's colder, darker, and more mysterious. The neat stripes and spots you saw earlier begin to fade into a more chaotic swirling mess. Imagine a washing machine spinning in slow motion while someone dumps syrup into it. Here, water and ammonia start to play their part. You've got heavier cloud systems, thicker, denser, and far less photogenic. Scientists believe there are layers of ammonia, ice hydrogen sulfide, and even water ice lurking down here. These are the weather systems that fuel Neptune's infamous storms, big brooding pressure systems that spin in eerie silence. And beneath that, well, it's hard to say. We haven't seen it. We can't even guess with confidence. Neptune's atmosphere blends gradually into what might be a slushy mantle of icy materials water, methane ammonia, all compressed under incredible pressure. It's not a solid surface. You'd fall in slow at first, then faster until molecules themselves started acting weird. Your atoms would get uncomfortably cozy. Now here's a delightfully strange tidbit. Under extreme pressure, scientists think the methane in Neptune's lower layers could break apart, releasing carbon atoms that then bond into diamonds. These diamonds would fall like rain, glittering stones, drifting downward through the depths. A storm of gems. Romantic, if not a little terrifying. The idea is still debated, but lab experiments suggest it's possible. And Neptune, ever the diva, would totally be the planet to accessorize its weather. Back in the upper atmosphere, things are still moving. The white methane clouds can form shockingly fast, sometimes appearing within hours. It's like the planet just gets an idea, spins up a new cloud, and lets it ride the jet streams like a cosmic food delivery. But these clouds don't just follow the rules. They sometimes bunch up in strange places, riding the edges of dark spots, or clustering where no model predicts they should. Scientists still argue whether these clusters signal deeper convection currents or are simply quirks of Neptune's fast rotation. It's all so precise, yet so completely unpredictable. Neptune isn't chaotic in the way a thunderstorm is. It's chaotic in the way jazz is improvised, elegant, slightly smug. And speaking of smug, there's a little fun fact. Neptune emits more energy than it gets from the sun. We've mentioned this before, but it bears repeating. Despite being nearly frozen by our standards, Neptune has an internal heat source, strong enough to keep its atmosphere boiling with motion. And while we know it's radiating heat, we don't know exactly how. Some theories suggest gravitational compression. Others say leftover heat from its formation, or even radioactive decay. The scientific jury is still out drinking lukewarm coffee and arguing quietly about thermal dynamics. Meanwhile, you float through the middle cloud layer, watching tendrils of ammonia ice spiral past. Occasionally, a burst of turbulence rips through, sending columns of gas twisting upward like elegant ghost tornadoes. You don't hear anything, of course. There's no sound in space, just motion. Gentle, relentless motion. If you reach a hand out, don't worry. Metaphorically, you could almost feel the texture of Neptune's air cold, sharp damp with frozen methane. Like fog that bites back. And through it all, the planet keeps spinning. Smoothly, quietly, without fuss. You begin to sense a rhythm to it, a lullaby written in jet streams and frost. Neptune doesn't rage. It hums. It simmers. It curates its storms with precision, then lets them fade like forgotten thoughts. You close your eyes just for a moment. But Neptune's weather doesn't sleep. It continues without you, patient and unhurried. Voyager 2 didn't know it was about to witness a planetary magic trick when it arrived at Neptune in August 1989. After all, it had already visited Jupiter, Saturn, and Uranus places, bursting with drama rings, moons, and magnetic fields, flexing like stage lights. But Neptune was different. It didn't strut. It didn't demand attention. It just sat there quiet and blue, like the cool kid in the back of the class. And Voyager, bless, It was the only guest at the show. You glide beside the spacecraft, now watching as it hums silently through the edge of the solar system. It's not fast by cosmic standards, but in human terms, it's zipping along at over 38,000 miles per hour. And yet, despite the speed, everything feels slow here. The sunlight is a whisper. The background stars barely move. Neptune looms larger and larger in the window, a cold giant wearing clouds like a silk scarf. Voyager 2 made history here. It's the only spacecraft to have flown by Neptune, and it did so at a distance of just under 3,000 miles from the planet's North Pole. That might sound far, but in planetary terms, it's like brushing against someone's coat on the subway. For 5 days, Voyager studied Neptune. That's all. 5 quick days, and then it was gone. But in that time, it captured some of the most hauntingly beautiful images of any planet in the solar system. And more than that, it revealed a side of Neptune no one had expected. Those storm systems, spotted for the first time by Voyager, the Great Dark Spot. A complete surprise. The winds measured and logged those impossibly fast gusts that nobody had even guessed could exist in a place so cold and dark. Voyager showed us Neptune not as a sleepy ice ball, but as a world of motion elegance and quiet fury. One of the more charming aspects of the Voyager mission is how analog it feels by today's standards. The data was beamed back in slow, choppy packets transmitted over a 4-hour delay. Scientists would receive grainy photos and build mosaics by hand, like assembling a jigsaw puzzle, one blurry tile at a time. It took patience, coffee, and probably more than a few sleepless nights, but the payoff, glorious. For the first time, humanity saw the whole planet in motion. The rotating cloud bands, the delicate rings, yes, Neptune has rings, and the dim but dramatic lighting that gave Neptune its signature ghostly look. One researcher described it as watching the Earth from a dream. Another just stared at the photos for hours, probably trying to decide whether Neptune was majestic or just playing it really, really cool. Voyager 2 also flew by Neptune's moon Triton more on that mysterious little rebel later, but even from that icy satellite, Neptune looked mesmerizing. Its blue atmosphere wrapped the planet like a silk curtain rippling with jet streams and shadowed by drifting white clouds. It didn't matter that there was no thunder, no lightning, no camera-shaking theatrics. Neptune didn't need noise. Its silence was part of the performance. Here's a mainstream fact worth remembering. The images Voyager sent back showed that the Great Dark Spot was about the size of Earth and had wind speeds clocked at over 1,000 miles per hour. That's enough to tear apart most buildings on Earth, if there were buildings to tear apart. But unlike Jupiter's Great Red Spot, Neptune's storm seemed less anchored. Scientists still argue whether its placement near the equator made it unstable, or if it simply lacked the depth needed to last. And then there's the quirky part. Voyager also discovered small bright clouds near the Great Dark Spot, high-altitude methane ice clouds that looked like little companions scuttling around the edge of the storm, like party guests too nervous to dance. They added texture to the mystery, hinting at updrafts and hidden currents beneath the surface. One of the lesser-known debates at the time was whether these bright clouds were temporary flukes or permanent features. Some researchers thought they could serve as signposts for deeper, longer-lasting structures. Others suspected Neptune was just being playful, creating clouds to mess with our expectations. After all, with only 5 days of footage, who could say, even now, when you hover in your imaginary pod, retracing Voyager's path, you can feel the sense of awe that must have hit the mission team. Neptune wasn't supposed to be interesting. It was too far too cold, too faint. And yet it revealed itself in layers like a shy artist, suddenly deciding to post their portfolio online. Perhaps what's most poignant is that Voyager 2 couldn't stay. After its brief encounter, it slingshotted away and kept going deeper into interstellar space. No return trip, no do-over. The data it collected remains our most detailed snapshot of Neptune to this day. Hubble and other telescopes have peeked in since, but from Earth's orbit, it's like trying to read a novel by candlelight from across a football field. So here you are, following Voyager's trail 5 billion kilometers from home, staring at a storm that no longer exists. The planet rotates slowly beneath you, its clouds curling and vanishing in elegant arcs. You drift along the jet streams, catching echoes of a moment that passed in 1989, and realize how fleeting it all is. In the grand timeline of the universe, 5 days is a blink. And yet Neptune chose that moment to open the curtains and show us something beautiful, something strange, something worth remembering. From your silent perch far above the planet, time bends a little. Neptune rotates below in its 16-hour rhythm, spinning like a perfectly tuned music box no one's touched in centuries. But you're not alone in your stargazing, now somewhere far behind you, drifting softly through Earth's orbit. The Hubble Space Telescope watches too. Hubble doesn't zip or roar or land. It just floats, clicking slow snapshots of the cosmos with the patience of a librarian. Since Voyager's quick flyby, Hubble has taken over the role of Neptune's long-distance pen pal, checking in every few years like a forgetful friend who still sends postcards. In 1994, 5 years after Voyager's visit, Hubble peered out toward Neptune again and blinked. The great dark spot, gone. Not reduced. Not drifting away. Gone. Erased from the planetary stage as if it had never existed. In its place, clear, clouded blue. You could almost hear scientists drop their pencils. Poof. Neptune had deleted a storm the size of Earth like a browser history tab. Then just a few years later, a new dark spot appeared. A different shape, a different location. This time, farther north. And over the following decades, Hubble captured a slow parade of similar features, each one swirling, each one temporary, each one obeying its own invisible clock. The storms didn't rage or flash. They simply existed, and then didn't. Here's a mainstream fact to cozy up with. Since Voyager's visit, Hubble has confirmed at least 6 new dark spots forming and disappearing on Neptune. These aren't small weather hiccups. They're massive high-pressure systems, strong enough to generate shock waves in the atmosphere. And yet, despite their power, they arrive and fade with almost no warning, like shy performers at an open mic night who quietly sneak off stage. What's charmingly frustrating is how slow the process looks from here. Earth orbits the Sun every 365 days, give or take. Neptune takes 165 years. That means a Neptune season lasts about 40 Earth years. When Hubble captures an image of a storm drifting from mid-latitude to the equator, that migration may take decades. You're not watching weather here. You're watching climate in slow motion. You're watching a whisper that takes years to finish a sentence. And as for the tools we use, Hubble is good, but it's no replacement for a flyby. Its vision limited by Earth's atmosphere and orbit only captures Neptune as a distant, blurry jewel. Spotting a storm on Neptune is like noticing a wrinkle on a bedsheet halfway across the street. You can see it, but don't expect detail. Still, Hubble persists, clicking patiently every year or so, building a photo album of Neptune's mood swings. Now, for a quirky detail, one particular storm in 2020 seemed to defy expectations entirely. It started like the others, drifting westward in the southern hemisphere, but then instead of fading, it reversed direction. It turned around and started heading back east. Scientists still argue whether this means the storm bounced off an unseen atmospheric boundary, or if the underlying currents shifted direction beneath it. Neptune naturally offered no comment. Even stranger, that rebellious storm had a smaller companion, a kind of mini vortex that followed it around like a lost puppy. The two danced together for months before the smaller one faded. For a planet made of gas and ice, Neptune sure knows how to put on a subtle duet. You might think we'd be used to the mystery by now, but every time Hubble zooms in, Neptune adds another twist. A storm appears where there shouldn't be one. A cloud breaks up, then reforms. Sometimes the whole planet seems to shift in tone, lighter, darker, more vivid, like it's adjusting a filter no one knew it had. Fringe theories have bloomed in response. Some researchers suspect deeper thermal cycles could be driving these changes internal, heat rising, venting energy through dark spots that act like safety valves. Others suggest magnetic field anomalies might influence storm formation in a way we don't yet understand. And yes, a few brave theorists have proposed that Neptune's upper atmosphere might be influenced by solar activity, despite receiving only a whisper of sunlight. These debates don't end. They just change direction, like the storms themselves. And here's something lovely to imagine. Because Hubble only checks in every year or two, we're missing a lot. In between each snapshot, Neptune could be throwing a full meteorological rave and cleaning it up before we arrive. Storms may rise and fall in just a few months, unseen and unrecorded. The ones we do catch, they're the long-living stragglers. The party guests who stayed a little too long and got caught by the camera. So you sit beside Hubble now, metaphorically speaking, and look out at this impossibly distant planet. You remember Voyager's flyby, and you compare it to this slow-motion photography session. It's like trying to follow a ballet through a series of postcards. But even in those limited frames, Neptune reveals something astonishing. A quiet, deliberate weather cycle happening at the edge of our solar system. A drama unfolding in silence. No thunder, no lightning, just spots that appear, drift, reverse, and vanish. It's not flashy, it's not fast, but it's undeniably beautiful. If you hover long enough above Neptune's surface, watching the clouds stretch, twist, and shuffle, you'll begin to notice something odd. The big storms, those dark swirling ovals, don't just spin in place like polite whirlpools. No, they drift. Slowly. Almost reluctantly. And where do they drift? North. Always, it seems north. Now, you might be tempted to blame Neptune's odd personality for this. But there's actually something deeper going on. The storms, those famous great dark spots, and their lesser-known cousins tend to migrate toward the equator, or poles, over time with a weird favoritism for the northern hemisphere. They don't go in straight lines, mind you. It's more of a meander. Like a dog following a scent that only it can detect, they wander pulled subtly by forces we only halfway understand. At the heart of this migration lies Neptune's system of jet streams. These are high-speed bands of wind that wrap around the planet like invisible belts, some racing east, others rushing west. It's a delicate dance, and these bands are stacked in latitude one on top of another like rows in a very aggressive sushi conveyor belt. Now imagine a massive storm gets spun up in the mid-latitudes. It starts drifting along with the wind until it bumps into another jet stream moving in the opposite direction. And that's when things get funky. Scientists still argue whether these boundary zones between jet streams act like barriers nudging the storm upward, or if internal forces within the storm like latent heat or vorticity, yes, that's a real word, drive the movement. The storms might be trying to find equilibrium, or maybe they're just surfing atmospheric waves we can't yet see. Either way, they tend to spiral northward, following the invisible scent trail of Neptune's meteorological mood. Here's a mainstream nugget. This storm migration is so consistent that Hubble has used it to predict where future storms might end up, and usually the predictions hold. Not always, though this is Neptune we're talking about. It's like trying to predict what your cat will do after it knocks a glass off the table. There's a general pattern, but it always throws in a surprise. A particularly odd case involved a storm that appeared in the southern hemisphere just as Voyager was waving goodbye in 1989. Over time, it didn't stay still. It drifted toward the equator, and instead of breaking apart, as Earth storms do when they leave the comfortable confines of their pressure zones, it kept its structure for quite a while. This confused scientists. Storms aren't supposed to do that. They're like toddlers take away their routine, and they fall apart. But Neptune's storms are made differently. They're anticyclones, high-pressure systems that spin the opposite direction of hurricanes on Earth. Instead of sucking air in, they push air out from the center, keeping themselves coherent and, dare we say, oddly stubborn. This push helps the storm fight against turbulent surrounding winds, like a slow-moving boulder in a stream of very confused minnows. Now for the quirky bit, some researchers have proposed that Neptune's internal rotation may not be uniform, meaning the planet might not spin as one tidy spherical object. Instead, different parts of its interior might be spinning at different rates. Yes, really, a planet with a slight identity crisis. And if that's true, it could explain some of the weird drifts and storm behaviors we observe. Still, the migration patterns remain elusive. Some storms wander up and vanish. Others shrink, drift sideways, then suddenly reappear days later in a different band. Scientists still argue whether there's a hidden system to this, some deep logic embedded in Neptune's layers, or if we're just watching random atmospheric jazz with no conductor. Another fun observation: these storms don't seem to cause much disturbance as they move. On Earth, when a large storm system travels, it can leave trails, trapped heat pressure ripples, and exhausted cloud systems in its wake. On Neptune, nothing. The storms glide across the planet like whispers. You'd never know they'd passed if you weren't watching them directly. You descend slightly now, following the edge of one such migrating storm. It doesn't roar. It doesn't pulse. It simply turns slowly within itself, like a massive carousel in the clouds. You drift with it, tracing its path northward. The winds pick up around you, jet streams whipping past like lanes on a cosmic highway. From this vantage, Neptune's North Pole begins to come into view, dim, faintly lit by the faraway sun. It's not an easy place to study. No spacecraft has visited the pole up close. No telescope has seen it in full daylight. It exists mostly as a blur, a mystery wrapped in blue, and yet this is where many storms seem to be heading. Why? Maybe something about the polar jet streams pulls them in. Or maybe, just maybe, Neptune's poles are places where these storms can finally rest, where the tension between pressure systems softens and the giant vortices lose their grip. It's a peaceful image. Storms having spent months drifting silently across the planet, reaching the poles and dissolving into mist. You can almost picture it, a slow, swirling ballet of wind and gas fading away in the pale polar twilight. No crash, no explosion, just a gentle unraveling. Neptune continues spinning. Another storm begins to form at mid-latitudes, and the cycle begins again. You sink now, not quickly, but gradually into Neptune's deeper atmosphere beyond the high, sparkling clouds and gentle jet streams. Down here, things are darker, thicker. Pressures rise, temperatures shift, and the world becomes quiet in a new way. Denser, heavier, almost secretive. And in this vast, unseen region lies one of Neptune's strangest contradictions. It gives off more heat than it gets, but it's still freezing. Let's start with the basics. Neptune is on average 255 degrees at the top of its clouds. That's so cold your eyelashes would freeze solid before you had time to blink. And yet Neptune radiates about 2.6 times more energy than it receives from the sun. That's not a rounding error. That's a planetary furnace smoldering beneath a frozen sky. So where is all that heat coming from? And why does the planet look like it couldn't toast a marshmallow if it tried? One mainstream theory is residual heat. Picture Neptune's birth, roughly 4.5 billion years ago, a violent formation from dust rock and gas collapsing under gravity. That collapse generates heat, intense compressive heat, and the gas giant's thick atmosphere may have been slowly leaking that energy ever since. It's like a planet-sized thermal blanket that never quite cooled off. But even that doesn't fully add up. Uranus, for instance, had a similar start, but it barely radiates any extra heat at all. Scientists still argue whether something deeper or even internal is at work in Neptune that isn't in Uranus. An invisible mechanism, a buried power source. Now here comes the delightfully weird part. Some researchers have suggested that Neptune's interior might contain a layer of superionic water. Yes, that's a thing which acts like a solid and a liquid at the same time. Imagine black slushy ice that conducts electricity like metal. This exotic material could help transfer internal heat in strange, unpredictable ways, sort of like lava wearing a tuxedo. Others suspect that radioactive decay might be contributing. Not much, just a whisper of warmth from deep within the core. But when you're surrounded by frigid emptiness, even a whisper matters. A small decay here, a particle there, and suddenly you've got a simmer going that lasts billions of years. Still, even with those ideas, Neptune remains one of the biggest head-scratchers in planetary science. Why is it so warm inside while its cousin Uranus stays as cold and quiet as a forgotten salad? The planets are nearly the same size, same mass, same composition. Yet Neptune is a furnace and Uranus is an ice cube. Scientists still argue whether Uranus experienced a catastrophic impact that knocked its internal structure askew, maybe a lopsided formation that broke its convection cycles. In contrast, Neptune might have formed more cleanly, allowing its heat to rise and escape more efficiently. And speaking of rising heat, here's where things get really funky. That extra energy fuels Neptune's wild weather systems. Think of it like a stovetop burner beneath a pot of gas and ice. The heat rises, stirring storms, powering jet streams, and keeping clouds in motion, even when solar energy is laughably scarce. In fact, some researchers have modeled Neptune's internal heat flow and found that it may be directly responsible for the formation of those mysterious dark spots. The heat wells up in columns, destabilizing the upper atmosphere just enough to trigger massive high-pressure systems that spiral into being. It's the planetary version of a low-key grudge bubbling into a full-blown outburst. Want a fringe tidbit? Some speculative models suggest there could be a layered convection system at play, where heat doesn't flow upward in one smooth movement, but in distinct steps or regions. Hotter zones and cooler zones separated like layers in a cake, each one convecting at its own pace like slow-motion lava lamps stacked on top of each other. If true, this would create regions of weather zones that are warmer, stormier, or cloudier than others, dictated not by sunlight, but by internal tectonics made of gas. And still, you float. Deeper now. The pressure begins to crush, hypothetically speaking, but you're safe in your dream. Around you, the blue fades into a deeper, darker shade, almost purple. Light is gone now, swallowed by thick clouds. You can't see the storms anymore, but you can feel the movement, the heat rising, the great pulsing breath of a planet that doesn't speak, but hums softly from its core. It's a strange kind of warmth, not the kind that invites you to take off your coat, but the kind that reminds you something is alive down here. Not alive like trees, or fish, or bacteria, but alive like pressure, like energy, like planetary motion. It stirs ever so slowly, building, dissipating, forming weather far above. Somewhere in this stew of hydrogen, helium, and methane, the heat climbs up molecule by molecule. Maybe it forms a plume. Maybe it fuels a new storm. Or maybe it just escapes into space unnoticed. You start to rise again. Up through the layers, the temperature drops, the pressure eases, and the clouds turn blue once more. Somewhere beneath you, the warmth remains. Neptune, cold on the outside, burns gently within. Not with flame, but with mystery. And above, high in the sky, another dark spot has started to form. Back above the clouds, you float gently over Neptune's glossy surface, watching the upper atmosphere swirl like cream in a cosmic teacup. Everything seems to flow logically. At first glance, winds spinning west to east storms drifting lazily northward. But then you remember something a little unsettling. Neptune's magnetic field is weird, not just quirky or eccentric, but truly almost rudely weird. It doesn't line up with the planet's rotation, not even close. And unlike Earth, whose magnetic field emerges neatly from the north and south poles, like a science fair diagram, Neptune's field is tilted by a whopping 47 degrees. That's like trying to wear a hat that keeps sliding over your face. Even stranger, the magnetic center isn't even in the middle of the planet. It's offset, like Neptune lost a bet and had to carry its magnetic field off to one side. This has baffled scientists for decades. If you tried to model this behavior with a spinning globe and a pair of magnets, you'd end up throwing it across the room in frustration. So what does all this mean? For starters, it suggests that Neptune's internal structure is complicated. Most planets with a magnetic field have a clear source, a liquid metal core spinning to generate electric currents. Earth, for example, has a dynamo created by molten iron and nickel in motion. But Neptune doesn't have a typical metal core. It likely has a hot, slushy ocean of ionic material, think ammonia water, and methane under ridiculous pressure, forming a sort of electrically conductive goo. That goo seems to generate Neptune's magnetic field. But because it's not neatly centralized, the field becomes lopsided, creating regions of stronger and weaker magnetism across the planet. It's like Neptune decided that symmetry was boring and opted for avant-garde interior design. And that's not just an aesthetic quirk. This off-kilter magnetism might play a role in Neptune's atmospheric behavior. though scientists still argue whether the effect is direct or merely coincidental. One line of thinking is that the magnetic field influences the way charged particles move in the atmosphere, subtly shaping wind patterns or guiding where storms form. Another theory suggests that the magnetic field's wonkiness is just a symptom of deeper chaos below the surface, like a leak in the plumbing, revealing where the whole system is under pressure. Want a fringe theory to spice things up? Some researchers have speculated that Neptune's odd magnetic field could point to an unstable interior layer that slowly sloshes over time. Imagine a great churning ocean of conductive material deep below the clouds, drifting unevenly as the planet spins. If true, this would mean Neptune's magnetic field might change shape over centuries, gently wobbling and shifting like a sleeping giant adjusting in bed. And now, for a quirky comparison, if you placed a compass on Neptune, hypothetically, let's not send your camping gear out there. Just yet, it wouldn't point toward the pole. It would spin twitch and generally give up on life. The magnetic field lines loop and swirl in odd directions, sometimes bending back into the planet at angles that defy common sense. This magnetic confusion could also affect the auroras, those glowing bands of light caused by solar particles hitting the upper atmosphere. On Earth, auroras gather neatly around the poles. On Neptune, they're scattered weak and kind of moody. They flicker in unexpected places, far from the poles, following magnetic lines that go off at sharp angles. It's as if Neptune's auroras got tired of the rules and started a jazz band in the wrong hemisphere. But the big question remains, is this magnetic oddness connected to Neptune's mysterious vanishing storms? Scientists still argue whether the field interacts with the atmosphere at all. On some gas giants like Jupiter, there's a strong connection between the magnetic field and weather phenomena. On Neptune, that connection is more elusive. The field is stronger than Earth's, yes, but its unusual shape may scatter its influence, making it harder to trace direct effects. It's like trying to track ripples on a pond when someone keeps flicking it from 12 different directions. Still, if magnetic anomalies influence heat flow, they could affect storm generation indirectly. Areas where magnetic activity is high might allow heat to escape more efficiently, creating updrafts and pressure differences that fuel new vortices. That's one idea anyway. Another says that storms themselves may cause small changes in local magnetic fields by disturbing the atmosphere's charged particles. For now, the best we can do is observe. Track the storms. Watch the auroras. Monitor the way Neptune continues to be well. Neptune tilted off center and unapologetically unpredictable. And yet, despite all this, the planet maintains a quiet kind of dignity. You look down on it now, and nothing seems amiss. The clouds still swirl, the blue still shimmers, and the jet streams march in their silent paths. But beneath the surface, a crooked compass spins, and the field lines stretch in directions you'll never see. It's a reminder that planets, like people, often carry their complexities on the inside. Neptune just chooses to wear its mystery with a little more flair. You glide now toward the upper atmosphere again, where the sunlight, faint though it may be, hits the planet just right. The clouds are thinner here, wispier, delicate like frosting swirled on a barely lit cake. And for the briefest moment, you catch it a shimmer. Not a bright, obvious sparkle, but a quiet twinkle, like ice catching light in the distance. Some might say you imagined it. But on Neptune, that's just how the magic works. Let's talk about clouds specifically. clouds that sparkle, or might, maybe. Scientists still argue whether Neptune's clouds ever genuinely glitter, but the ingredients are certainly there. Up in the frigid top layers of Neptune's atmosphere, methane is abundant. And when methane cools, like really cools, it condenses into crystals. Methane ice. Think of them as tiny frozen prisms, drifting lazily across the sky. Now combine that with the planet's weak but persistent sunlight, and you've got a recipe for some seriously understated atmospheric bling. It wouldn't be like diamonds glinting in a spotlight, though. More like glitter stirred into fog. Soft, subtle. A background shimmer like static in an old television show you can't quite look away from. And here's where things get juicy, or perhaps crunchy. Under enough pressure, deep in Neptune's mantle, some researchers believe that methane doesn't just freeze, it breaks apart. The carbon gets squished so intensely that it rearranges into a crystalline structure. That structure, diamond. Yes, Neptune might be making diamonds. Not one or two, mind you, but potentially rains of them. Picture this thousands, maybe millions of diamond crystals forming under extreme pressure and falling through the icy layers of the planet like gemstones tossed into a wishing well. They wouldn't survive to reach the core, they'd likely vaporize or dissolve before they landed anywhere, but the idea of diamond rain has captured scientific imaginations for decades. The lab experiments that inspired this theory involved compressing hydrocarbons under high heat and pressure until diamonds began to form. When scientists tried to recreate Neptune's interior conditions, diamonds appeared tiny ones to be clear, but enough to suggest the theory isn't just poetic fluff. It's science with sparkle. Of course, that's deep below. Up here, where you're floating in the blue hush of the upper atmosphere, the clouds are made of methane ice and possibly hydrogen sulfide. Yes, the same molecule that gives rotten eggs their charming scent. So while Neptune might sparkle quietly, it probably doesn't smell like roses. Luckily, space has no air, so the scent stays hypothetical and politely out of reach. Neptune's high-altitude clouds tend to gather near storm systems, particularly around the great dark spots and other pressure centers. These clouds often appear as bright white streaks or patches standing out against the darker blues below. Scientists have spotted them drifting ahead of storms, like banners indicating where vertical motion is strongest, rising plumes of gas and ice being pulled upward by invisible fingers. But sometimes, clouds appear where no storm is present at all. They just form and drift, following patterns we don't understand. This has led to speculation that Neptune's weather isn't just vertically layered. It may have invisible waves, like the ripples you see when a stone is dropped into water. These atmospheric waves could cause clouds to form spontaneously, like thoughts appearing in a half-asleep mind. Here's a lovely fringe theory. Some atmospheric physicists think these waves might interact with solar wind particles, causing faint flashes of luminescence in the upper layers, Neptune's version of airglow. Not quite auroras, not quite lightning. Just soft pulses of light flickering like memories in the haze. We haven't confirmed them yet, but Hubble's sensitive imaging has hinted at irregular brightness that isn't fully explained. Now for something more grounded literally. Scientists have long wondered why Neptune's atmosphere has such distinct layers of clouds rather than one big uniform soup. Turns out the different gases present like methane, ammonia, and hydrogen sulfide all condense at different temperatures and pressures. That means, as you go down into Neptune's atmosphere, you pass through separate cloud decks, each made of different materials. It's like a cosmic tiramisu if tiramisu could swirl at 1,200 miles per hour and occasionally flash ultraviolet light. The top layer, methane. Below that, possibly ammonia. Deeper still, water maybe. Scientists still argue whether the water clouds exist at all or whether the pressures involved would squish them into something else entirely. One study even proposed that some clouds could form without condensation, just through pressure alone in a process that defies easy categorization. You drift alongside one such cloud deck, now gliding above a field of pale cottony forms stretching from horizon to horizon. Each cloud looks soft, but you know better. They're made of ice so cold it could snap steel. And yet they swirl with a grace that feels almost gentle. You imagine yourself reaching out just barely to touch one. The chill would be instant. The crystal structure, if visible up close, might look like feathers made of glass or lace frozen in midair. You wouldn't see sparkle in the way we do on Earth. Neptune's sunlight is too faint. But here and there, just a glint, a flash, a whisper of brilliance in the blue. So, do Neptune's clouds sparkle? Maybe. Maybe not. But as you float above them, surrounded by silence and methane frost, you realize something sometimes not knowing is better. Sometimes it's enough just to drift, to imagine, to look down on a planet where ice might glitter and diamonds might fall, and feel the strange, sleepy comfort of a mystery left unsolved. You continue your descent, passing layer after icy layer of Neptune's vast atmosphere until the familiar blue haze fades into something darker, thicker, more ancient. You're approaching the part of the planet no one's ever seen, not through a telescope, not from a spacecraft, not even in the most detailed simulations. Welcome to the heart of the mystery, the center of the blue giant, Neptune's core, if it exists at all. Let's start with the mainstream theory. Neptune, like most planets, is supposed to have a core. That's what the textbooks say. A solidish ball of rock and metal, probably about the size of Earth, hiding deep beneath thousands of miles of swirling gas and slushy ice. This core would have formed early in Neptune's history, collecting dust and debris before gathering enough mass to pull in hydrogen, helium, and methane, turning into the big cold whirlpool we know today. But here's the problem: we can't see it, can't detect it directly. And even our best models don't agree on what's down there. Some say it's rocky, others say it's icy. A few even suggest it may not be solid at all, at least not in the way we understand solids. Scientists still argue whether Neptune has a distinct dense core, or if the pressure and heat have blurred the lines between layers, creating a gradual transition from gas to slush to something else. The term you'll hear tossed around is fuzzy core, like a scoop of ice cream left out too long, not quite liquid, not quite solid, a weird pressure-cooked blob that defies labels. This idea turns planetary structure on its head. On Earth, we like our cores firm, crust-mantle core done. Even gas giants like Jupiter and Saturn are thought to have relatively clear internal boundaries. But Neptune shrugs at your expectations. It doesn't do tidy. It does gradients, layers that blend, shift, and melt into each other under pressures that make steel behave like butter. Here's a quirky scientific tidbit: pressure at Neptune's core may reach 7 million times the atmospheric pressure on Earth. That's the kind of squeeze that makes molecules act weird. Hydrogen under these conditions might turn metallic. Water could become a superionic fluid, a state of matter where hydrogen atoms flow like a liquid while the oxygen atoms remain locked in place like a crystal lattice. It's not science fiction. It's a real thing. We've even made tiny amounts in labs. So imagine this beneath the serene, spinning clouds of Neptune lies an ocean not of water, but of hot, dense, electrically charged sludge. Not sloshy like a sea, but syrupy, sluggish, pulsing with ancient energy. And somewhere inside, maybe there's a core, not a sharp edged sphere, but a dense, hot lump of whatever survived the planet's turbulent youth. And here's where things get even sleepier. The existence of the core doesn't even matter that much for the surface weather. Neptune's storms, winds, and jet streams are powered mostly by heat rising from this unseen region. Whether it comes from a hard core or a warm, gooey center, the result is the same convection. Rising heat, atmospheric chaos, all of it driven by something you can't see and may never touch. Fringe theory time. Some have wondered if Neptune's core could be slowly dissolving. Over billions of years, the high temperatures and crushing pressure might be breaking down the rocky materials and blending them into the surrounding icy layers. The line between core and not core blurs, a sort of planetary soup. This could help explain Neptune's strange magnetic field too, since the electrical conductivity of that soup might vary in ways we haven't yet modeled. Still, some researchers remain hopeful for clarity. They argue that gravitational readings, subtle changes in the way Neptune tugs on nearby objects, suggest the presence of a dense center. Not well defined, perhaps, but definitely there. A ghostly heartbeat beneath the haze. And what about missions? Surely, with all this mystery, someone wants to go back and check. Yes. Oh, yes. Several mission concepts have been proposed. Orbiters, atmospheric probes, even a Neptune clipper modeled after the Cassini mission to Saturn. These spacecraft could map the gravity field dive into the atmosphere and maybe catch a whiff of what's going on below. But for now, they remain blueprints, PowerPoint, slides, and daydreams. So for the foreseeable future, Neptune's core remains a bedtime story for planetary scientists. A tale of heat and pressure and material states that don't play by the rules. You float now above this hidden world, imagining it dark, crushing, silent. Maybe solid, maybe not. Maybe glowing faintly from within. But even without answers, there's peace in the mystery. Not every planet needs to be solved. Some are best left to drift their truths, tucked away under miles of blue and ice, waiting patiently for curious minds and the next brave spacecraft. Neptune spins. The winds howl. And somewhere deep below, something warm and heavy stirs. You drift higher now, back toward the comforting glow of Neptune's outer shell, letting go of the dense, unseen core, and rising into air that's thin enough for sunlight, faint as it is to whisper across the clouds again. The atmosphere relaxes here, softens. And off to your right, something comes into view. Not a storm, not a cloud, but a moon. Triton, Neptune's largest moon. And frankly, one of the strangest moons in the entire solar system. It doesn't orbit like the others. It doesn't spin like the others. It doesn't even behave like it wants to be there. You approach Triton slowly. Its surface glows pale pink and white, a frozen landscape pocked with ridges and dark scars. From here, it seems peaceful. But make no mistake, Triton is a cosmic rebel, and it has stories to tell. Let's start with the obvious. Triton orbits Neptune backwards. Most moons orbit their planets in the same direction. The planet rotates like ducks swimming in a whirlpool. But Triton goes the other way. Retrograde. like a dancer who turned left when everyone else turned right. It's one of only a few large moons in the solar system to do this, and it's a giant blinking neon sign that says, "I didn't form here." Scientists believe Triton was once a dwarf planet, something like Pluto, floating through the Kuiper Belt, minding its own business. Then Neptune came along. Gravity did its thing, and suddenly Triton was captured, pulled into Neptune's orbit. But this wasn't a gentle adoption. The process likely caused chaos, disrupting Neptune's original moons, triggering collisions, and sending some smaller satellites flying off into space like bad roommates evicted by a new landlord. Triton's arrival was, in cosmic terms, a hostile takeover. Here's a mainstream fact. Triton is the seventh largest moon in the solar system and the only large moon with a retrograde orbit. This makes it incredibly important to planetary scientists. It's a frozen record of the outer solar system's wild youth. Studying Triton could help us understand how giant planets interact with smaller objects and how chaos sometimes leads to strange, stable beauty. But Triton isn't just a weird orbit. It's also geologically active. Despite being frozen on the outside, the moon shows signs of internal warmth. In 1989, during its flyby, Voyager 2 captured something shocking: geysers. Yes, actual geysers spewing nitrogen gas miles into space from beneath the ice. The plumes were subtle, more like whispered exhalations than volcanic blasts. But they revealed something remarkable beneath that frosty surface. Something was stirring. Scientists still argue whether these geysers are powered by subsurface oceans, radioactive decay, or sunlight warming dark patches on the surface that absorb heat and cause sublimation. Some even suggest a combination of all three. But whatever the cause, the result is clear. Triton is alive. Not biologically necessarily, but geologically. It's a moon with breath. And what does this have to do with Neptune's storms? Good question. You see, Triton's presence affects Neptune in more ways than one. For starters, its gravitational tug adds subtle distortions to Neptune's gravitational field. These distortions can influence how material in Neptune's atmosphere flows ever so slightly, nudging cloud bands or affecting tidal forces deep below the surface. Additionally, Triton's past could be tied to Neptune's mysterious heat. If its capture disrupted the system dramatically, it may have helped shift Neptune's axis-triggered internal friction, or even added energy that still hasn't fully dissipated. Scientists still argue whether Triton's arrival helped shape the planet's weather as we know it. An invisible hand gently stirring the pot long after the spoon was set down. Here's a fun, quirky observation. Triton's surface looks weirdly smooth in some areas, like it's been ironed. This suggests active resurfacing, possibly from cryovolcanism, a delightful word that basically means ice volcanoes. Yes, on Triton, you might get eruptions of liquid nitrogen or ammonia oozing across the crust and freezing into new terrain. Imagine lava flows, but in soft pastels. Even its temperature is extreme. Triton is one of the coldest objects in the solar system, averaging about 235 Talmudix. Yet despite that chill, it remains strangely dynamic. It's like a ballerina dancing gracefully on a stage made of dry ice. And while you're floating, here gazing at Triton's quiet rebellion, you can't help but wonder, what else does it know? Has it seen Neptune's storms from above? Has it watched the great dark spot appear, vanish, then reappear again over decades? Does it feel the pull of those deep winds twisting silently below? Probably not. But it orbits Neptune every 5.9 days, passing close enough to cast a shadow on the clouds from time to time. And when it does, perhaps for a few minutes, the planet's atmosphere stills, just slightly. Triton is a moon out of place orbiting a planet that doesn't behave, covered in frost, that moves and cracks and exhales. And somehow, that makes it perfect. A fitting companion for Neptune, a planet of hidden cores, mysterious storms, off-center fields, and shimmering clouds. As you drift back toward Neptune's upper atmosphere, you glance once more at Triton, spinning backward into the night. It doesn't wave goodbye. It just keeps going quietly, rewriting the rules of what a moon can be. Back above Neptune now, your gaze returns to the planet's clouds, the soft swirls, the streaks of methane white, the gently drifting storms. They move like they always do, calm, quiet, confident. But don't let the graceful pace fool you. Behind those clouds lies a different kind of chaos, one that doesn't howl or flash, but simmers in silence. You see, here's the truth. When scientists try to simulate Neptune's atmosphere, things start to fall apart, literally. The best computers, the most sophisticated models, the math we trust to guide spacecraft to the edge of the solar system. None of it quite works when applied to Neptune's disappearing storms. It's like trying to explain a magic trick with physics and being left holding a calculator and a headache. So, what's going on? It starts with the basics. We know Neptune's atmosphere is layered. We know there are jet streams. We've seen storms form and vanish. But when we plug all this into simulation software feeding in data from Voyager Hubble and decades of ground-based observations, the models don't behave. They either produce storms that never vanish or ones that dissolve far too quickly. There's no sweet spot, no reliable recipe. Scientists still argue whether our equations are missing a key ingredient, some unknown feedback loop, a chemical quirk, or maybe a gravitational hiccup deep below the clouds. One mainstream approach involves vortex dynamics, trying to model how large spinning systems like Neptune's dark spots interact with surrounding winds. On Jupiter, for example, the Great Red Spot survives because it's protected by bands of wind that help stabilize it. Neptune has similar wind bands, but their spacing and speed seem to destabilize storms instead. So when we try to simulate a great dark spot, it often fizzles out early or drifts into the wrong zone and falls apart. Another issue, Neptune's internal heat. As we've discussed, the planet radiates far more energy than it receives from the sun. That heat rises, driving convection columns of gas that push upward, fueling cloud formation and storms. But when we model that convection using Earth-based logic, it doesn't work well. On Neptune, convection might not rise in neat vertical plumes. It could be tilted, twisted, or even layered. Imagine smoke drifting sideways, caught between invisible sheets of pressure and magnetic force. And then there's the wild card, microphysics. That's the fancy term for what tiny particles, ice crystals, dust grains, chemical compounds do inside clouds. On Neptune, microphysics is still mostly guesswork. What shape are methane ice crystals? How do they cluster? How quickly do they form and fall? These tiny details affect how clouds look, move, and interact. Get the microphysics wrong, and your simulation becomes a foggy mess. Some models show clouds dissipating too fast. Others make them too sticky, too reflective, too stable. You might be thinking, well, surely artificial intelligence could help, right? It has. Kind of. Machine learning has started to tease out some patterns in Neptune's cloud data. Algorithms can identify recurring shapes, wind speeds, and storm migrations. But even AI gets confused when a dark spot appears in one year and is gone the next without leaving a trace. Neptune doesn't like being predictable, not even for the robots. Here's a delightfully quirky tidbit. One simulation predicted that a Neptune-like planet with its winds and heat, but no magnetic field, would be more stable. That's right. Some models think Neptune's magnetic field might actually destabilize its weather patterns. The same twisted magnetism that drives its auroras and warps its compass may also be making the weather weird. Scientists still argue whether the field is strong enough at cloud level to affect circulation, but the coincidence is suspicious. Now imagine you're running one of these simulations. You've coded for temperature gradients, wind velocity, vertical shear, and radiative cooling. You press run and your storm spins off course and vanishes, or your vortex splits in half and floats into a region that shouldn't support it. Or worse, you get nothing at all, just a blank screen with sluggish currents and no drama. Meanwhile, back in reality, Hubble peers down and spots a dark spot forming again in almost the same location as the last. A storm no model predicted. A system no code could generate. This isn't a one-time glitch. It happens over and over. The models and the data don't quite line up. They're like two musicians playing different songs at the same tempo. You can almost see the connection, but it never clicks. Neptune plays its own tune, and we're still learning the notes. And maybe that's the most Neptune thing of all. Here's the planet calmly spinning, letting its storms appear and vanish like ghost ships in a fog, while our best efforts to decode it fall just short. And in that shortfall, there's wonder. There's space for imagination, for dreams, for the quiet joy of not knowing. So you sit back, still drifting, still watching. The clouds below continue their soft spiral. The models continue to break, and you realize sometimes mystery is the best lullaby of all. As you coast above Neptune's slowly spinning horizon, another dark patch begins to take shape far below. At first, it's just a smudge, a shadow in the sea of blue. But then it starts to stretch, lengthen, swirl, a new great dark spot. Well, maybe not great just yet, but certainly dark, and certainly familiar. This is not your first time seeing one. If you've been keeping count, and Hubble certainly has, this is perhaps the 6th or 7th such storm spotted since Voyager's iconic sighting back in 1989. Like a traveling actor stepping into the same role in a long-running play, the new storm arrives, without fanfare, follows the same cues, and begins its performance on Neptune's celestial stage. You lean in closer. The spot is a broad oval rotating counterclockwise in the southern hemisphere. A high-pressure system, much like its predecessors, with a calm, dark interior surrounded by brilliant high-altitude clouds, those bright companions that tend to tag along like paparazzi, chasing a celebrity who's too tired to run. One mainstream fact in 2018, Hubble spotted a dark storm in Neptune's northern hemisphere for the first time in recorded history. Until then, all major storm systems had appeared in the south. This northern upstart seemed to break the rules, and then just as quickly it began to fade. Scientists observed something unusual. As the storm moved closer to the equator, it reversed direction before vanishing. Yes, it changed course, backtracked, a meteorological U-turn, which no model had ever predicted. Now, as you hover, you're witnessing a similar phenomenon unfold again. The spot forming below is migrating slowly, but where and how long will it last? These are the questions researchers ask each time a new spot appears. Will this one disappear in 6 months, or linger for 5 years like Voyager's storm? Nobody knows. Neptune isn't telling. There's something almost ceremonial about the process. The storms arrive like clockwork, except the clock is broken, and the schedule is a guess. Scientists still argue whether there's a seasonal pattern to it. Neptune's year lasts 165 Earth years, so a single Neptune season could stretch across decades. Are these storms part of a long, slow weather cycle, or are they just random outbursts from the planet's restless interior? The answer may lie in recurrence. Some storms form in the same region where others vanished years before. It's as if the atmosphere remembers, like the imprint of a storm remains etched in the deeper flows, just waiting for the right conditions to reawaken. One theory suggests there could be persistent upwelling zones, places where heat rises more strongly from the interior, triggering storm formation over and over, like a volcano without lava, just gas, swirling forever. Here's a quirky little twist. One recent dark spot appeared without the usual bright companion clouds. This confused observers. The clouds typically ride along the leading edge, forming where air is being pushed upward. Their absence raised eyebrows. Was this storm shallower than the others, weaker? Or was it simply too young, not yet developed enough to show its plumage? These inconsistencies, the missing clouds, the shifting directions, the varying lifespans, have led scientists to revisit their assumptions. Maybe there isn't one type of dark spot. Maybe there's a family of storms, each with different traits, some strong, some fragile, some born deep in the atmosphere, others just skimming the upper layers like weather tourists. Neptune, it seems, might not just be spawning identical systems, it's experimenting. And speaking of experiments, let's not forget that Neptune is the only planet in the solar system where we regularly watch this phenomenon of storm birth and death in action. On Jupiter, the Great Red Spot is enduring a centuries-long tantrum with no end in sight. But on Neptune, these systems rise and fall within a human lifetime, sometimes within a school year. They're fleeting, poetic, and just a bit mischievous. There's a quiet beauty in that. These are storms you can miss. You blink. You go about your day, and when you look again, they're gone. It's a reminder that even planets massive and distant know how to do ephemeral really well. Still, each new storm brings opportunity. Astronomers aim their telescopes. They compare. They contrast. They draw little red circles on grainy images and say, "There, that's new." Some observatories even try to watch Neptune over multiple nights in a row, something tricky to do when it's billions of miles away and rotating every 16 hours like it's got somewhere to be. But slowly, a pattern emerges. Not a perfect one. Not yet. But hints. Ghosts of consistency. This storm might follow the same path as the last. It might behave just differently enough to teach us something new. And as you drift above, watching the spot grow larger, darker, more defined, you feel it. Neptune is telling a story, not in words, not even in thunder or lightning, but in swirls, in shadows, in storms that whisper, "I've been here before." You smile and wait to see what this one will do. You float above Neptune now, just beyond its limb, where the thin atmosphere fades into deep space like a watercolor into darkness. The newest storm below continues its patient spin, vast, silent, and magnificent. But you're pulling back, slowly, letting the planet rotate away beneath you, as if turning the final page of a very long, very soothing book. It's funny, isn't it? This place, this storm-blasted, ice-shrouded, wind-battered sphere, is technically the windiest planet in the solar system. Wind speeds that could strip paint from steel jet streams, that roar across latitudes, and storms that appear without warning and vanish without a goodbye. On paper, Neptune should be chaos incarnate, but when you watch it, it's calm, even serene. It's a trick of distance. A storm, moving at 1,200 miles per hour, looks slow from 5 billion kilometers away. The thick atmosphere muffles every twitch and turn. No sound escapes. The violence is all tucked neatly beneath a blanket of methane blue. And that's the final mystery tonight. How can the windiest place feel so strangely still? It starts with Neptune's structure. With no solid surface, the planet doesn't have mountains or oceans to interrupt its jet streams. The winds simply circle, forever, like clock hands on a watch without gears. This lack of friction makes Neptune's weather systems eerily efficient, smooth, symmetrical, like they've been practicing in secret. But the other half of the calm, that's ours. It's the calm that comes from watching something so distant, so slow, that it forces you to slow down too. There's no breaking news from Neptune, no daily briefings, no trending hashtags, only long looping cycles. Whispered heat rising from a blurred core. A sideways magnetic field tracing strange arcs through frozen clouds. And a moon orbiting backward like it knows something we don't. Here's a final quirky tidbit. If you could somehow stand in Neptune's upper atmosphere, ignoring the deadly cold, the pressure, the lack of a floor, you wouldn't hear the wind. It would rush silently past you. There's no ground to rattle, no trees to shake. The air moves too fast, too high, too smoothly, like silence in motion. Some scientists have said that watching Neptune is like listening to a whisper in a cathedral. You don't always catch the words, but you feel them. They linger. They echo in the back of your mind long after the voice has stopped. So, as you rise now, slowly backing away from the planet's edge, you carry with you the softness of it all, the quiet drama, the elegance of clouds that swirl, disappear, and return in new forms, the grace of a planet that could tear itself apart, but chooses instead to spin in peace. Let Neptune keep its secrets. Let it sparkle in blue and storm in silence. You've seen enough for one night. Now let's wind things down. You begin to drift even farther. Now the planet shrinking below you, like a marble sinking into deep velvet. The stars stretch out again. No storms here. No jet streams. Just space. Quiet. Infinite. Still. Neptune remains behind you, barely a dot, its blue light fading into the background of the cosmos. But it lingers in your mind, its calm clouds, its gentle chaos, its quiet storms still turning far below. It no longer feels like a planet. It feels like a thought, a mood, a place made not of gas or gravity, but of softness. The silence deepens. Your breath slows. There's nothing left to chase now. No answers to hunt. Just drifting, floating, letting the questions settle like dust on an old telescope lens. Maybe in the end that's what Neptune offers. Not certainty, but space to wonder. You're wrapped in it now, in quiet and distance and stillness. No buzzing alerts, no ticking clocks. Just the hush between stars. Let your limbs grow heavy. Let the thoughts slow. Let the winds that howl across Neptune drift past you far below, quiet as the night. Close your eyes. You're safe. You're still. You're stardust again. Good night, traveler.